Hello, everyone. This presentation is for the Rutgers Alternate Route Program pre-service course. This is just a reminder that all time used for videos, student reflection periods, and guided practice is cut to achieve the time limit. All right, thank you and enjoy. Welcome, students of my AP Chemistry Period 4 class. Today we'll be doing a presentation on atomic structure and properties. This material lines up with Unit 1 of the AP curriculum, as well as Chapter 3 of your textbook. All right, so today we're going to be reviewing average atomic mass, definition of a mole, molar mass, percent composition, empirical formulas, and molecular formulas. These concepts are going to look familiar to you as you went over them in honors chemistry, but they're also concepts you're going to be seeing on the AP exam, so we'll be reviewing them today. Before we begin, I asked anyone if they had any news they wanted to share to help keep us connected during this virtual time, and a couple people did write in. So Margaret is actually turning 17 on Sunday, so congratulations, Margaret. Happy birthday, and good luck on your driver's test. That's really exciting. Matthew will actually be doing some work on his Eagle Scout Award and his Eagle Scout project, actually. So that's also exciting. So we wish him luck. And if there's any way we can help you, Matthew, definitely let us know. All right, let's get started. Okay, so the first 20 minutes of the lesson, it's going to be me lecturing to you, and you can ask questions at any time. I'll be asking for your participation at various time periods. And then we are going to do a guided practice where you're going to get to solve a murder mystery using the concepts you learned today. All right, so here you see 4 different substances. The alignment is a little messed up, but it's sugar, salt, water, and vinegar. Now, just based on what you see, how would you put them in order based on their weight? And then I want you to also ask yourself, what do all 4 items have in common? So you can put that in the comments. All right, so now you can see the weights, and in order, it would be water, then vinegar, then salt, and then sugar. And as far as what they all have in common, I got a couple of answers that were true, but not necessarily what I was looking for. Like they all have weight, they all can be seen, they all have matter. These are great answers, but I was looking for was an answer that quite a few of you got, and that is that they're all 1 mole of substance. So very impressive, guys. Good job. Okay, I hope you enjoyed that video. It's one of my favorites. So now we're going to be thinking about, all right, what if I wanted to know how much 1,000 water molecules weigh? Well, that's something we're going to be able to figure out soon, but let's start with something we can visualize. So let's look at how much does 1,000 hazelnuts weigh. So I had a couple hazelnuts in my kitchen. I weighed them out and got the masses that you can see here. All right. Now, if we want to know how much an average hazelnut weighs, we're just going to find the average of these masses. So can someone quickly add up the total mass? All right, 13.98, good. Okay, so we're going to divide that by 10. We get 1.398, which we can round to 1.40. And we can say that's the mass of an average hazelnut. So that doesn't mean that every hazelnut weighs 1.40 grams. It means that if you took a large quantity of hazelnuts and divided them by the number of hazelnuts, 1.40 is going to most likely be your average, okay? And so if we want to know how much 1,000 hazelnuts weigh, we'd say 1.40 times 1,000. So we'd say it's 140 grams, right? We can expect 1,000 hazelnuts would weigh 140 grams. Now, if you've ever actually looked at a bag of hazelnuts and check out this next time you go to the grocery store, you'll often see 28 grams or about 20 hazelnuts as a serving size. So that makes sense based on what we just calculated, right? So that's pretty cool. All right, thanks. Okay, so we can actually use a very similar method that we use for the hazelnuts to look at the atomic weights of elements. So let's look at carbon. So the first thing we want to do is identify the natural abundance of carbon, and we have those numbers here. So there's 3 isotopes of carbon that we can find on planet Earth, and it's 98.89% carbon 12, 1.11% carbon 13, and we're not really going to count carbon 14 because it's pretty rare and barely is factored in. Okay, so now we can say that if we can use that percentage and the weights of those individual isotopes and say, all right, 0.9889 times 12 AMU and 0.011 times 13.0034 AMU gives us an atomic average of 12.01 AMU, meaning that one carbon atom we would expect would weigh around 12.01 AMU. All right, so now we've talked a little bit about the mole, and we want to know, where did the concept of the mole come from? 6.022 times 10 to the 23rd seems a little bit random, right? So it actually means that in 12.01 grams of carbon, there are 6.022 times 10 to the 23rd carbon atoms. So this actually defines the mole. So for 1 mole of carbon, there's 6.022 times 10 to the 23rd carbon atoms, and it's 12.01 grams of carbon. Now, the mole, as far as the amount, is always constant. It's always 6.022 times 10 to the 23rd. But the weight is going to change based on how heavy individual atoms or molecules or whatever you're trying to find are. And then if you notice on the periodic table, you actually see a 12.011 underneath carbon. So that stands for 12.011 AMU, the weight of an individual carbon atom, or it could stand for 12.01 grams, which is the weight of a mole of carbon atoms. So here is a mass spectrometer. It's currently the most accurate tool we have for comparing masses of elements, and it uses 4 steps. So the first step is ionization, where atoms or molecules are passed through a beam of high-speed electrons, which knock electrons off of the atoms or molecules and charges them into becoming positive ions. The second step is acceleration, where the electric field accelerates these ions. And the third step is deflection. So the accelerated ion produces its own magnetic field, which changes the direction of the ion. So the most massive ions are going to be deflected the least. So if you see that metal plate called a detector plate at the end of the picture, that is where the masses are going to be recorded. That information is going to be printed out, and you'll see a series of peaks, and those peaks can be used to determine what isotopes are present and what their relative abundance is. So we're actually going to be looking at this in one of your upcoming labs. Okay, so if we have 15 grams of nickel and we want to know how many moles are in 15 grams and how many atoms are in 15 grams, then this is how we're going to solve it. We're going to say 15 grams of nickel times 1 mole of nickel over the weight of 1 mole of nickel, which is 58.69 grams. And that's going to give us 0.256 moles of nickel. So all we're doing here is going back to stoichiometry. All right. So now if we know we have 0.256 moles of nickel, we can then multiply that by our Avogadro's number, or the term mole, 6.022 times 10 to the 23rd atoms. And we end up finding that we have 1.54 times 10 to the 23rd atoms. Now, what if we have the opposite problem? We know how many atoms we have, but we want to know how many moles we have and what the mass of our sample is. So we're told we have 10.0 times 10 to the 21st atoms of calcium. So we can then divide that by a mole, 6.022 times 10 to the 23rd, and we find out that we have 1.66 times 10 to the negative 2 moles of calcium. We could then take that amount and multiply it by the mass of a mole of calcium, which we'd find on our periodic table, which is 40.08 grams of calcium. And we end up finding that we have 0.665 grams of calcium. Okay, so the mass of a substance, or the molar mass of a substance, is the mass in grams of 1 mole of compound. So we can break that apart and say, all right, if we want to know the mass of 1 mole of carbon dioxide, then we can say the mass of 1 mole of carbon plus the mass of 2 moles of oxygen is going to be equal to our molar mass. So I represent this in circles here. So you see the orange circle is carbon, the blue circles are oxygen. So it's really just simple addition. All right, so we have the mass of 1 mole of carbon is 12.01 grams. The mass of 2 moles of oxygen would be 2 times 16 grams, which is 32 grams. And then the mass of 1 mole of carbon dioxide is 43.01 grams. So what's important to note, though, is if you have an ionic formula, say you have barium carbonate, and you would look at barium and then carbonate on its own. You wouldn't consider carbonate its own molecule. So you can just use the molar mass of carbonate times as many as you have. And if you don't know the molar mass of carbonate, you would figure it out using this method and then apply that to your next equation. Okay, so let's look at a problem calculating molar mass. So juglone is a dye. It's also an herbicide. It comes from the husk of black walnuts, which grow on a black walnut tree. We sometimes can see black walnut trees up in the East Coast, but they're native to the southern areas in the eastern side of the United States. So if we want to look for the molar mass of juglone, we're going to use our formula that we were given, C10H6O3. Then we can use the same process we used in the previous slide and say, all right, let's look at the periodic table. Carbon weighs 12.01 grams, hydrogen weighs 1.008 grams, and oxygen weighs 16 grams. So we're going to take each of these masses and we're going to multiply them by as many atoms as we have. So 10 times 12, 6 times 1, 3 times 16. We get those masses and we add them up to find the mass of 1 mole of juglone is 174.1 grams. So now if we're told that we have a sample of 1.56 times 10 to the negative second grams of pure juglone, we want to know how many moles we have. All right, so we take that 1.56 times 10 to the negative second grams, and then we can just divide it by the molar mass and say, okay, it's divided by 174.1 grams. That gives us 8.96 times 10 to the negative fifth moles. Percent composition of compounds. So if we want to look for the mass percent, we're going to use the same technique we use to find the percent of anything. Part over whole times 100%. So we're going to say the mass of an element in the compound divided by the mass of the whole compound times 100%. So let's look at an example. If we want to find out the mass percent of carbon in CO2, we're going to say the mass of carbon divided by the mass of carbon dioxide times 100% equals 12.01 grams over 44.01 grams times 100%. So the mass percent of carbon in carbon dioxide is 27.29%. So if we want to determine the formula of a compound, there are some tools we can use if it's an unknown that we really don't know anything about the sample. So here is actually a combustion device. You see a furnace where the sample goes in. It's then heated and oxygen is pumped in, so you have an excess of oxygen. Now, the way it works is that any hydrogen present is going to react with oxygen to create water, which is then absorbed. And any oxygen carbon present will also react with the oxygen, and CO2 will be present which will be absorbed by sodium hydroxide. All the other oxygen and gas will be discarded, but we can determine how much hydrogen is present and how much carbon is present, which will help us if we're trying to identify an unknown molecule. So compounds can have two different types of formulas. The first type is the empirical formula. This is going to be the simplest formula for a molecule. It's the simplest whole number ratio. So if we look at the example of carbon dioxide, uh, the amounts of atoms are not divisible by any numbers. They're already the lowest ratio. And then we have the molecular formula, which is typically the real formula for a molecule. So that's going to be equal to the empirical formula times a whole number integer. For example, C3O6. This is really 3 times CO2, where CO2 would be our empirical formula and C3O6 would be our molecular formula. Now, if CO2 was in fact the molecule we were talking about, the empirical formula and the molecular formula would be the same in that case. But for C3O6, that's our molecular formula, and CO2 would be our empirical formula. Okay, so let's try a problem. Let's look at empirical and molecular formula. So if we want to find the empirical and molecular formula of an unknown compound that has a composition 40% carbon, 6.71% hydrogen, and 53.29% oxygen, the first thing we want to do is assume we have 100 grams. That will mean that we have 40 grams of carbon, 6.71 grams of hydrogen, and 53.29 grams of oxygen. We then are convert all of these gram weights to moles. So we find out we have 3.33 moles of carbon, as well as 3.33 moles of oxygen, and 6.66 moles of hydrogen. So whatever is your least molar amount, you're going to divide each of the other molar amounts by that number. So you're going to divide each of these by 3.33. And we find that we have 1 carbon, 2 hydrogens, and 1 oxygen. This means our empirical formula is CH2O. So then we find the molar mass of this empirical compound. And we would find that it's 29.02 grams if we found the molar mass of that molecule. Well, we can, according to the problem, our molar mass is actually going to be 180.16 grams per mole. So what does this tell us? It tells us that our empirical formula is not our molecular formula. So to find the molecular formula, we're just going to take that larger molar mass and divide it by the molar mass of our empirical formula. We end up finding that it's about 6. So we take that empirical formula and we multiply each atom by 6. So our new molecular formula is C6H12O6, which is actually the molecule fructose. So our mystery compound is actually fructose. Okay, so that's it for our lecture portion of today. You're going to download the document attached to this slide and begin your guided practice. I will be here and available to answer any questions you have. Good luck.